All right, are there any, actually, let me say first, our third exam is a week from today. Today and Friday we'll work hard. Monday we'll talk about the exam. Wednesday you'll take it. We've gone through a few sections of the book. Today will be another one where the online homework is not really adequate. And as I've done before, I've posted some problems that you should absolutely take a look at. I've actually made an assignment out of it, which I can add in your homework grades, and we'll see how we process it. Maybe I'll put you on the honor system, and you tell me if you did your best, I'll give you full credit. We'll see. Because I really, really want you to know, to have the experience with those problems, because they are going to show up on the exam. Okay, some like them. Are there any questions on the homework? Yeah, and the homework for today, I supplemented, and make sure you look at those. I keep saying it. I posted some problems from another book that I like a lot, and you may have noticed, I think I've solved 3 of them. I've posted solutions. These are not videos, these are photographs of the work I did on my market board, and I hope you can follow them. If you have any advice for how you could follow them easier, or if you have other problems you would like me to write a solution to and post, I'm perfectly willing to do that. I think one of the problems I posted, it's even one of the ones I put on the assignments. Don't start by looking at what I post. Start by trying to solve the problem, because if you just read what I did, it's not going to help you. But if you try to solve it first, and maybe you'll solve it all the way, then just check it against my answer, see if you got it right. If not, then you can hopefully, track down where did I make a mistake, and pay careful attention and never make that mistake again. Okay? Any questions? All right. Today we start a new chapter, doing the same sorts of things. Looks like I can go about there. And if I start writing outside these lines, somebody let me know. Out there. Chapter 6. Something called power series. In section 1, we'll just kind of introduce the basics. Here's what a power series is. We're going to take a formula, a sequence, and we're going to assume that for every n, the values are non-negative. And then we're going to form this series. Summation. The index information doesn't really matter. In x to the n. Think of it as a function of x. It is a function of x if it converges. If it doesn't, then it's nothing. Okay, and we want to answer this question. For what x values does it converge? You may remember on the homework, it was the first one in the online homework, and I wanted you to do it, so I signed it. If I were making the homework myself, I would put it towards the end because it's a fairly challenging problem. But you had a problem, something like this. Maybe some number 5x to the 2n equals 13. Solve for x. Remember that problem? Yeah, so that's kind of the thing here. We put a very, there you're finding one particular x value for which it converges. Here we want to find all of the values for which it converges. Okay, so that problem kind of is a nice setup for what we want to do here. So there are basically three tools that we can use, tools that we develop in chapter 5 to answer the question. One of them will be the predominant one we'll use. Okay, we use three tools to answer the question. The first one, the most important one, is the ratio test. The coefficients are non-negative, but x, it can be any real number, positive, negative. And so if you look at the series, like our ratio test only really, as we find, it only works on series with non-negative terms in it, not negative ones. So we're going to modify the test just like we're going to make it work for absolute convergence. It doesn't really change anything we do. It just allows us to extend the test to series like these. Second is the root test. Maybe it's never ever our go-to test, but it's possible. And we'll also need to modify it for absolute convergence. And the third one, like if we're really lucky, it depends on the nature of the ANs, the coefficients of our powers of x. It could be that that series is geometric. And then, we know everything there is to know about geometric series. So we use what we know. Now, with that said, I could end up with one that's actually geometric. Never think about this. Use the ratio test. It'll work perfectly fine. Okay? But if we see it, maybe it'll make life easy for us. All right. So I'm primarily, in fact, I think every example I'll do in class today is going to be about the ratio test. We're going to use the ratio test to answer that question. Okay, and it turns out there's structure in the answer. What is there? Like three possibilities, three things that can happen for every single power series. Lands into one of these three categories. So we'll make sure we've identified all of those and understand how to recognize when they occur. All right, so here's what we're going to do. First, let me write out, see what's going on here. I'll write the index information. I'm going to start at 0 and write out our power series. That's a power series. When we have the x, and so we're asking you a question, when does it converge? In fact, there are two kinds of power series. The one I'm talking about, we say in x. And in a minute, I'll show you a different one. It turns out that we can solve the new one. The other one, by the way, we're learning how to solve this one. So it's just kind of a technicality. All right, and if I write the terms out, I get something that looks like a polynomial. I get a constant a0, let's say 1x, let's say 2x squared. It's not a polynomial because there's no degree. The powers go on and on and on. It's an infinite series. But you can see it looks kind of like a polynomial. Right? So my advice so far is we're going to use the ratio test. So let's see what happens. Using the ratio test. Now remember, we're using just a little slight modification. We're going to apply the ratio test to a series of absolute values. That's what absolute convergence refers to, right? I evaluate the limit as n goes to infinity. The n plus first term. And because it's for absolute convergence, those guys are never negative, so I can just write them down. The x's could be, so I need to make sure we make them positive to the n plus 1. Let's plug in n plus 1 over here. It shows up there. Show it there. Divide by the nth term, the ratio test. Okay. Nothing really new yet. Maybe we're applying it to for absolute convergence. What happens to the absolute values of x? How many in the numerator? How many in the numerator? How many powers of the absolute value of x? N plus 1. How many in the denominator? N. I can cancel all the ones in the denominator with all but how many of the ones in the numerator? 1. So I've got an absolute value of x left over. There's no n's there. I can push it through the limit sign. Then I have the limit as n goes to infinity, a n plus 1 over a. So the three possibilities depend upon that limit. Okay, I'm going to call that limit L, and then we'll investigate what the important conditions on L are. And while I wrote a symbol that looks like a number L, we're going to leave open the possibility that this limit may not exist. So L may not be a number, maybe infinity. We'll talk about it. Julian.
So is x a constant?
Okay, so think of this as a function. Here is the function, and we're just trying to find the value of x. So it has nothing to do with n. X and n just moves me down the terms, and so we're trying to find the values for which it converges. Okay? The first possibility. There are 3 possibilities. Cases. There's only 5 letters in cases. How about I wrote 6 possibilities? First one, L equals 0. So the limit, the absolute value of x times 0. Okay, I just got what we figured out over here. Plugged in my 0, case 1. Now, we're using the ratio test. How do we conclude the ratio test? Calculate the limit, and then if anybody out there? What's the conclusion of the ratio test? How does it tell us?
If L is greater than 1, it diverges.
If the limit is greater than 1, it diverges.
Yeah.
Anything else?
If it's less than 1, it converges.
Thank you for answering my question. Yeah. Well, we got 0. What does that mean?
Less than 1.
It's less than 1. Does it depend on x? Do we need certain x's to make it less than 1? No, we don't. It's 0 for all x. So the answer, over here I asked a question. And if this happens, it converges for all x. That's one of the possibilities. Second possibility. Does that make sense to you? The second one is if we get infinity. Because the a's are non-negative, the only way the limit can fail to exist May not be 100% true. It's going to happen for us though, because it's going to infinity. As we're talking about an plus 1 over an, the limit of that is infinity. And can we make that less than 1 for any x's? Yes or no? Well, x didn't show up here. Has no bearing. So we can't make the conclusion, our limit to the ratio test be less than 1. So our answer is there's one kind of technicality here. It only converges for x equals 0. Because if x equals 0, it's not an infinite series. It's a single number, right? That constant. All the other terms have an x. Plug in the 0, it's going to wipe them out. So trivially, every power series converges for at least one number. Does it converge for more? Not if this is the case. Okay, the third possibility, and that is where L is positive finite. Get a limit like 7. All right, well, let's remember the ratio test got us that quantity, and so we need to ensure that that thing is less than 1. It's all obviously never negative. And now we see it depends on x, that we can make that less than 1 for some x, probably not going to be less than 1 for other x's. And so we just solve this inequality, divide by L, unravel the it's not dyslexic if you write something upside down. Is there a name for that? I think a little bit ago I said, when I wrote this, I said, maybe it's 7. I think it's stuck in my brain. Anyway, 1 over L, which means x is between negative 1 over L and 1 over L. That's almost the answer to our question. For what x's does it converge? Well, it converges for all of these. Okay. What do we know about the ratio test? We apply it and get the value 1. What does that tell us about the series? Diverges, ratio test. Is that right? Diverges. You know, Ken? Converges? Ratio test. Get 1. Is that right? I know I'm an old man, but quite the way to do it. What do you think? Say it again. Say it louder. The test fails. So it could diverge, it could converge. Right? If we didn't have a power series, then we would say, oh man, I wasted all that effort. I did the ratio test and I got 1. It didn't help me. And then I have to go back to my list and say, well, let's try the integral test, or let's try limit comparison or something. But because this is a power series, what we have to do is, I'm guaranteed that it exists for every number in this interval. And then we need to investigate the endpoints. It could converge or diverge. The ratio test fails. And now, when we look at the endpoints, we're not looking at a power series anymore. We're looking at a particular series that could have been an exercise in chapter 5. And so we're going to run through our list of tests and say, which one does the job here? Is it the integral, or is it the limit comparison, or whatever? All right, we have some language we use to describe the 3 cases. Are there any questions? Jesse?
So how do we know what L is? Is that
Well, we calculate this limit. Do we know how to calculate limits? Absolutely, we're expert at it. So I'll do some examples. And maybe I'll do at least 3 examples. Boom, 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 right? So we can see how it works in all of them. Maybe. All right, notation, terminology, let's say. There are 2 things we like to talk about with respect to a power series. One of them is the radius of convergence. And it's different for all 3 cases. So these are the previous cases. The first one, and we're going to use the symbol R, capital R for this. It converges for all x, and so we'll just say R is infinity, the radius of convergence. Converges everywhere. The second one, we said, well, it only converges at 0. So there's no stretch. In the third case, for the notation that we've used over there, the radius is 1 over L. Like from 0, 0 is the center of the values for which it converges. We go up to 1 over L, we go down to minus 1 over L. So every number within 1 over L units of 0 is, we have convergence, except possibly the endpoints. Okay, and along with radius convergence, we have something called the interval of convergence. In case 1, it's just the real numbers. Minus infinity, plus infinity. R equals 0, there's really not an interval. If you want to write it as an interval, I suppose you could write it like that. We could also say, it only converges at x equals 0. We could also say it's a super boring series if it only converted at 0, like it's never going to be useful for us. We just want to recognize it. That's a possibility. The third case, there are 4 potential intervals. It could diverge at both endpoints. In which case the interval would be minus R to R open. It could converge at one endpoint and diverge at the other in either way. Or finally, it could converge at both. So one of those is the right answer for any given power series. If we land in case 2, oh, sorry, case 3. So for any given power series, that puts us in case 3. One of those is correct. The other 3 are close, but not quite. Jesse. Neither. The bracket means include that endpoint. The parenthesis means do not include that endpoint. So we call the first interval there, we call it an open interval. We don't include the endpoints. And the last one, we call it closed interval. The endpoints are in with it. And the 2 in the middle, we could call them half open or half closed, whatever. Questions? So I want to do at least 3 examples. But first, I want to introduce another kind of power series and show how we can, it's a more general power series and how we can immediately reduce it to the case that I've already told us about. And maybe one of the three examples I can incorporate that. All right. So remember this guy. I called him a power series in X. And some people would say, another name for it is a power series centered at 0. And you get a really good feel for that with these answers. That we get intervals that are all centered at 0. They go up R, they go down minus R. Maybe include the endpoints, maybe not. But it's centered at 0, the interval. Now, I want to talk about a slightly different one. It looks like this. X minus a to the n. So there's no subscript here. I can tell them apart from the coefficients. This is called a power series in X minus a. And it's centered at X equals a. So let's say that a is 3 and r is 2. Okay, so we're going to have an interval whose radius is 2, centered at 3. So we're going to go from 1, 2 units below 3, up to 5. 2 units is centered at 3, up 2 in each direction, maybe the endpoints. The endpoints they're not power series, they're a particular series that hopefully the things we learned in previous chapter will tell us what to do. They're just a normal infinite series. All right. So what we're going to do here is let u be x minus a, which turns it into one of those. We'll solve that one. Here are the possibilities. And then we'll just shift center to a. Again, I'll do an example. So it's no big deal if it's in x minus a. Everything we learn about these, that's all we need to know along with this substitution. All right, example. Find the radius and interval of convergence. For 3 power series. The first one. Summation n equals 0 to infinity, x to the n over n factorial. So we're going to use the ratio test. Calculate the limit as n goes to infinity. This is for absolute convergence. Absolute x to the n plus 1 over n plus 1 factorial. And like before, we will invert and multiply. Just like we did before when using the ratio test. The second example, we're not going to do that. I'll explain it when we get there. There's a really good reason. Notice the x's behave just like we talked about at the beginning. I have n plus 1 powers in the numerator. I have n in the denominator. All of the ones in the denominator get canceled. I have 1 left. I can pop it through the limit. So we can almost count on that happening all of the time, as long as our power series hits every power. Let's see what we have left here. It goes to infinity. I have an n factorial on the top and an n plus 1 factorial on the bottom. Somebody simplify that for me. over n plus 1. Yep. Even though we just learned factorials on Monday, they're pretty easy to work with. At least for this, what we need to do here. What's that limit?
0.
0. So the ratio test gets us 0 times the absolute value of x, which is less than 1. Does it depend on x? Does not. So this power series converges for all x. Therefore, we're in case 1. The radius is infinity. The interval is minus infinity. Jesse, your earlier question about parentheses versus bracket, maybe you were thinking of the fact that we never put the bracket on infinity, right? We never include infinity because it's not a number. So we always use parentheses. No.
Didn't you say that the only thing greater than n factorial would be n to the n?
So you're saying you know it goes to 0 right off the bat? Okay. Yeah, I guess what I'd like you to do is think that that's true, and then maybe do the work and show that it really is true. It's a little bit deceptive in that we do have exponential growth, x at the end, but you know that factorial beats exponential growth. Now, it may be that, I overstated it just a little bit. Factorial is the fastest rate of growth for physical processes that we know about. But you can invent others. Like n to the n, I've never seen a physical process where that describes what's really going on. But I know that one of the homework problems has 2 to the power n squared. Well, that's like exponential growth raised to the polynomial power or something like it. And when I see that, I don't really know how to think about it. I'm going to do the work. Is that exponential? Well, I'm not sure. I'm going to do the work and make sure. Okay, so we can invent all sorts of weird growth rates, but the ones that show up naturally, factorial is certainly the fastest growing one in life. Any other questions? All right, part B. Summation. Oh, by the way, we will show later in this chapter that this converges for all x. It actually converges to the function e to the x for all x. Kind of a fun fact. So imagine that you work for HP, you build calculators, and you need to tell this calculator how to find like e to the square root of 2. How do we do that? Well, one way is to turn that what do we call it, a transcendental function into just a polynomial. And you can plug your square root in there and just do addition and subtract powers, multiplication, and you get a value. So this is just a little bonus. We don't know it yet, but we'll discover it before too long. All right, here's my second example, opposite of the last one. And I'll also incorporate the second kind of power series. So what we're going to do, my advice over there is to like just substitute that away. Equals x minus 3, and so we get n factorial. Then we're going to use the ratio test, which is the limit as n goes to infinity. There's going to be an absolute value of u pop out for exactly the same reason that an absolute value of x popped out. I have n plus 1 of them in the numerator, in the denominator, and then what's left is n plus 1 factorial divided by n factorial. This is, I think, the only series we've seen so far. There might have been one on a homework assignment where the terms are not written as a fraction. And so, we've gotten used to skipping the first step and dividing by inverting and multiplying, right? But we don't need to do that here because it's just thing on top and the thing on the bottom. It turns out naturally. And what is n plus 1 factorial over n factorial?
N plus one.
N plus 1, and what is that limit?
Infinity.
Infinity. Can we make that less than 1? Can we choose a u value that's less than 1?
It'd be the reciprocal of L.
Yeah, so it would only be u equals 0, which this guy converges, no matter what this formula is, converges for 0. It's totally boring. So this guy's going to converge only at 0. Converge is not the right word because it's just a single value for the series. U equals 0. But remember the original problem. So we want to answer for this question. So we're going to plug in 0 and solve for x. So this guy converges only for x equals 3. Move the center from 0 to 3, the x minus 3. Questions? Part C. Summation. N squared. I had a really good in the morning class. 2 to the n. Oh no, I don't want to do that. N squared. Over n cubed plus 1. X to the n. So in the morning class, a student asked me a certain question, and I really wanted to answer this question. And so I chose as my third example, maybe the one, not the one I would have chosen, but because he asked the question, it was a good question. So for you guys, no one has asked me any questions. So I'll do the one that probably is the best one to do based on where we are. All right, so we're going to calculate the ratio test. Notice 3 out of 3 ratio test. We're going to find the limit as n goes to infinity. The absolute x's, again, one of them is going to pop out, right? The question that I was asking in the morning class is, does it ever happen where you can't just automatically write the absolute value of u or x in front? And there is a case. And so I made an example that answered his question. And then we have n plus 1 squared over n plus 1 cubed plus 1 more. Then we invert and multiply. Kind of a big mess, but I think it's easy to analyze. So the numerator, imagine multiplying that thing out. We're going to get what kind of a function in the numerator? A polynomial of degree 5 squared times the third power. How about the denominator? 5. How do we compute limits at infinity of a polynomial divided by polynomial when the degrees are the same?
Take the coefficients.
Leading coefficients. What is it in the numerator? Can you tell?
1.
And the denominator?
1.
1. Yeah, so you get the absolute value of x times 1. You have to be less than 1. So the radius is 1. That number right there, it's reciprocal basically. And we know so far it converges between -1 and 1, but we're not sure about the endpoints. Julian,
So how did x to the n become absolute value?
remember to use the ratio test, we have to make the terms be positive numbers.
Yeah.
And we also know from our work with alternating series that if a series converges in absolute value, we call it converging absolutely, then the original series converges. So I can find out information about this guy by investigating that, if I can get good information there, and we're getting good information. Okay?
Then why isn't it to the n power?
Okay, so remember, we worked the details out twice, and now it worked out the same both ways, so I'm asking you like maybe to go with me here. I'm going to get n plus 1 of them from the ratio test in the numerator and n in the denominator. So I can cancel all of these, and I'm just left with 1, and I push it through. Okay? And again, the question that I was asking in the morning class is, can we always do that? And the answer is no, not always. I'll show you when we can't do it. And you'll see. All right. So we've got the radius. We don't yet have the interval. We need to investigate the endpoints. There are 2 of them. The first one is x equals 1 in no particular order. The first one I chose is x equals 1. So we're just going to plug it in. And I get series n squared over n cubed plus 1 times 1 to the n. Well, that 1 to n doesn't do anything. And there is the series. Do we know the behavior of that series? Scott? You're right, we do know. Does anybody know how we know? It's basically a harmonic series. It's a polynomial over polynomial. The degrees differ by 1, right? And the harmonic series diverges. So this guy equals infinity. It diverges. And officially, the easiest way to verify that, I mean, Noah asked a question earlier, like, isn't it obvious? And I think this is almost obvious. But if your professor said, like, does this series converge or diverge? Show your work. Then here's what you would do. Limit compare it with the harmonic. And it'll work out perfectly fine. Okay, so down here we'll write the, if we don't know that yet, our interval -1, 1, and we know we can't include the right-hand endpoint, so we'll put a parenthesis. Now we'll focus on the left-hand endpoint, which is the summation n squared over n cubed plus 1 times -1 to the n. What kind of a series is that?
Alternating.
Alternating. So if it might still be like an alternating harmonic. I mean, we haven't lost the harmonic nature, n squared over n cubed. Does the alternating harmonic converge or diverge? It converges. Yeah. This is less than infinity. And officially, we can use the alternating series test. And the tricky part of it, we need to show that this function is eventually decreasing. And that might take a little bit of work, take the derivative, but it converges. So we include the left-hand endpoint. It converges there. We do not include the right hand. And there is our answer. radius is 1. We knew it converged inside here, but we need to check out the endpoints. So we do that work. And this one happened to converge at the left hand, diverge at the right. Remember earlier, I wrote those 4 intervals, and that was one of them. So that's the one that was. Are there any questions? David?
So, for a, for C, that's C.
Say it again?
So, for C, that's your.
Yes, yes it is.
Yeah. So for C3, we always check it. We check, we check it.
Okay, so the ratio test gets us the interior from -r to r. And all we have to do is check the. Okay. And knowing R doesn't tell us one thing about the endpoints. Just have to look at them individually. And here we had series that weren't very complicated, basically harmonic series. All right, so let's look at this one. What do we have, about 2 minutes left? So later on, we're going to have running the power series where the only powers that are present are the even numbers or the odd numbers. Okay, and we can represent it like that. So if n starts at 0, goes to infinity, then I plug in 0, I get a sub 0, and then I get a sub 1 times x squared, right? In times 1. And a sub 2 times x to the 4th. So it skips. In other words, the coefficients of the even terms or the odd powered terms, they're all 0. So we don't need to write them. Only the even ones survive. And then when I use the ratio test, just focus on the x part. Everything else is the same as it has been. I'm going to have absolute x to the 2 times n plus 1 and absolute x divided by to the 2n. Right? And then the other stuff, which is not one bit different than it was. That's what it is. When I go to cancel the x's, what happens? How many more do I have in the numerator than the denominator? Yeah. 2. Yeah, you got to distribute that too. So I don't take absolute x just out. I take the absolute value of x squared. And then deal with the limit. So again, the morning class, someone said, can we always just take absolute x out? If we don't skip terms in the polynomial-like form, then yeah, it'll work every time. If we do skip it, it's going to be we have to be a little bit careful. Then we can just work it out. We could also get, let's say this limit turns out to be the absolute value of x squared times 6. Well, we need that to be less than 1, right? This is the ratio test. If it's less than 1, the limit, it converges. So then I'm going to get, well, that means x squared needs to be smaller than 1/6, which means x need to land where? Between 1 over the square root of 6 and negative 1 over the square root of 6, right? All of these x's will get me an x that makes that true, which will then get us a value. I don't know if we'll see that in the homework. I haven't seen it yet, but I haven't looked very exhaustive. For this example, the radius is 1 over the square root of 6. And we don't know, can't find the interval because we never, it's all hypothetical. We didn't start with the power. Any questions? All right, so again, there are no problems on the XYZ homework. There's a photograph posted of problems from the textbook, and I will work some of them out. And again, if you have a suggestion, hey, I tried to do number 18, I can't get it, could you help me? Like maybe post a picture of a solution, let me know. I'd be glad to do that. I like solving calculus problems. So anything you think will help you, let me know and I can put it on there. I think there's only one there right now. But I might be wrong. All right, see you Friday.